In section 6.3, we're going to be discussing something called complex fractions. Now, complex fractions are basically just complicated fractions, meaning that they're big, nasty, ugly things. They're not always really big, but the idea, and we'll formally define this in the next part of your lecture. It's going to be something that has a fraction inside of another fraction, like fractions in the numerator, fractions in the denominator. So that whenever we see those kind of things, our goal is going to be to get rid of the complicated nature. That is, we want to simplify it. We want to turn a big complex fraction into a single ordinary rational function, rational expression. It's not going to take us very long to do this. This is a short section, but the main idea of this section is that we develop a technique that we're actually going to use again when we get into a later section when we start solving rational equations. That's going to be the most important section that we cover in this chapter, is being able to solve equations. That's what algebra is all about. But the nice thing, again, is we're going to see that same technique that we'll use later on here in a nice little simple section for us to cover. All right, so let's get started. The definition of a complex fraction is as follows. A complex fraction is one that has a fraction expression in its numerator or denominator, or both. So you got fractions inside fractions. So here's a few examples of what you might see. Something simple like x plus 1 over 2 divided by 3 over x plus 2 is a complex fraction. Notice how you've got a main fraction bar, which you can clearly see is larger than the other fractions. So you can tell by looking that you've got a fraction inside the numerator and a fraction inside the denominator. Another example might be something that looks like this: 1 over x plus 1 over y squared divided by 1 over y plus, say, x over y squared. All right? See? Fractions inside fractions. Now, there's a pretty big difference between the two fractions I've written on your screen right now. The first one, we actually have a technique for solving or simplifying that rational expression. It's called invert and multiply, because you've got one fraction divided by one other fraction. Now, it only is the case that inversion technique for division works if you have a single fraction that you're dividing by. In this case, we actually have two fractions in the denominator. We have the sum that's going to mess things up. We can't just flip the two of them simultaneously, because that does not accomplish the division operation when you have fractions in the denominator like this. Okay, let me show you one example that you actually may come across somewhere down the line in the real world, in terms of formulas that represent real scenarios, real quantities. Here's what it looks like. Take a variable a, say that's equal to some variable p divided by 1 minus 1 divided by 1 plus I, all raised to the nth power. This is a car payment formula. We'll probably talk a little bit about this later on when we get into chapter 11 and we look at a quick application of annuities. But in this case, this is a formula that can be used to calculate how much how much your payment is, if P is your payment and A is your amount and I has something to do with your interest rate. I'll go through the details here. If we're ever given an application where that actually shows up in the model, we'll define exactly what those are. But you can see in this particular application, in this formula, you do have a fraction inside of a fraction. There's one other example that I wanted to put up on the screen, and we're going to use this a little bit later on. Look at this one. X to the minus 1 plus x to the minus 2y, all divided by y to the minus 1 plus x y to the minus 2. All right, now looking at this, you see that, well, it doesn't at first glance look like a complex fraction. But if you recall a rule for exponent that you've seen somewhere before. What does it mean to have a negative exponent? If I have some number and I raise it to the negative power, what does that actually mean? And somewhere along the way you will have seen this. What that actually means is to take and divide by a to the n, meaning a to the negative n is the same thing as 1 over a to the n. So basically what you're saying with a negative exponent is to treat that as the denominator of a fraction. So for example, if I said 2 to the minus second, that actually is 1 over 2 squared, or 1/4. Raising something to a negative power doesn't mean take the negative of 2 to the second. It actually means to take 1 over 2 to the second, which is 1/4. It's basically a reciprocal. Now, whenever you see that show up inside a fraction like this, because of the plus sign, you can't just take that x to the minus 1 and move it all the way down to the denominator of the full fraction. You could only do that if the operation in between these two was multiplication. All right, what you've actually got to do is treat each one of these as its own individual fraction. That's a fraction. That's going to be one fraction. That's going to be one. This is going to be one, each separately. Okay, so x to the minus 1 is the same thing as 1 over x to the first, plus x to the minus 2 means there's going to be an x squared in the denominator. Y just has the first power, so it stays up in its numerator. Y to the minus 1 means 1 over y to the first, plus, and then y to the minus 2 here means, and notice by the way, there's an understood first power on that x. That minus 2 is not to both x and y, so you end up with x over y squared. So you're required to treat these as individual fractions in the numerator and denominator. So you see, when you see negative exponents, and we'll do some examples with this later on, you do get a complex fraction when you have negative exponents inside terms in an existing rational expression. Okay? Now, what's our goal? Our goal is going to be, can we take these kind of objects, all three of these, or four of these examples that I've given you here, can we convert them to simple fractions, not complex fractions? And let's take a look at those steps. To simplify a complex fraction, we're basically, there's two techniques that the textbook, if you were to read the textbook online, two techniques that the textbook will cover on how to do this. I'm going to show you just one, which I think is the best one, the quickest one, the one that works in all cases, and it also is the one that is the same technique that we will use later on when we solve equations. What we're going to start off by doing is finding the LCD of all the fractions within the complex fraction. That is, you're going to look at all the fractions in the numerator and all the fractions in the denominator and find the lowest common denominator for all those fractions. Then you're going to multiply both the numerator and the denominator of the complex fraction by the LCD. Same kind of technique you use whenever you were finding common denominators. Remember whenever you were adding fractions and had to turn them into the common denominator? The thing that you had to do there was to multiply something on top and bottom. There's a principle there that says you can multiply the same thing on top and bottom of a fraction and not change its value, right? So that's what we're going to do. And then the last step is we simplify if possible. So look at this example that you see right here. Now you've got three fractions inside there. We've got this one, and this one. Okay? Using those three fractions, we want to identify the LCD. What is the LCD for all three of those fractions? Okay? We know we need a 5, because that's in the denominator's fraction. We know we need an x, and the highest power that it appears is x squared. So now what we do is we multiply both sides of the complex fraction. We take 2 over x squared minus 3 over x, the numerator, times 5x squared, and we multiply the denominator, 5x squared. Now this is a nice little trick that works to get rid of those fractions. See, the nice thing about the common denominator is every single denominator will cancel with something in that denominator. So for example, if I let's take this 5x squared times the first term in the numerator. 5x squared times 2 over x squared. The x squareds cancel, right? Leaving me with 2 times 5, which gives me 10. Right? Okay. Now take that same LCD and let's multiply it times the second one. Now what happens there? Well, the x cancels with one of those, and I'm left with a minus 3 times 5x, which gives me 15x, divided by, and on bottom, the 5's cancel, and I'm going to be left with x to the 4th. And you'll recognize now I no longer have fractions inside fractions. That is a simplified complex fraction. That has the same value as the original fraction, only now it's in simplified form. Alright, the goal is to find the LCD and multiply the top and bottom, everything in the numerator, everything in the denominator, by the LCD. Okay? Alright, let's look at this one example. Do the same thing. LCD. In this case, where are my fractions? Now, notice there's no fraction in the denominator, right? There is a fraction, two fractions in fact, in the numerator. I don't need to worry about the 7 because it's not a fraction itself, right? I've already got rid of fractions. There are no fractions in the denominator of the complex fraction. So the LCD just needs to take care of getting rid of this x plus 7 and this x. So the LCD is going to have those two factors in it. I'm going to multiply on top by x and x plus 7. I'm going to multiply on bottom by x and x plus 7. Okay? Now if I take that times the first term in the numerator, the x plus 7's cancel, right? And I'm left with just an x. Now, I take that same LCD, x times x plus 7 times the second one, the x's cancel, and I'm left with a minus an x plus 7. Okay? In the denominator, I'm going to have x, a 7, and an x plus 7. Distributing the minus sign in the numerator leaves me with x minus 7 over 7x times x plus 7. Okay, now just in case you're wondering, the reason why I had to put the x plus 7 in parentheses is that I have multiplied by that entire factor. So that minus sign here is going to subtract everything that's left after the x cancel. Alright, x minus x subtracts out the 7, divides out with the 7 underneath, and I'm left with a negative 1 over x times x plus 7. Okay, and that is the final answer in that case. We have one last example in this section. This particular example goes back to the negative exponents that we talked about earlier in the section. Remember that whenever you see, for example, a to the minus 1, that's the same thing as 1 over a. So, looking at this first term in the numerator, we treat that as its own fraction. We rewrite it as 1 over a. Okay. On the second term in the numerator, we're going to have ab to the minus 2. Again, remember the a is to the first power, so it stays up on top, and then b to the minus 2 moves the b to the bottom, and it becomes b squared. That's what a negative exponent means. ab to the minus 2 in the denominator is the same term we just did, so I can rewrite that again as a over b squared minus, and now I've got a to the minus 2, b to the minus 1, so a to the minus 2 comes to the bottom and becomes a squared, b to the minus 1 comes to the bottom and becomes b to the first. There's nothing left on top, so there's an understood 1. Right? Whenever you moved everything, whenever you divided everything to the denominator, you're left behind with a 1. Alright, now we're ready to simplify. So the next step is, just like we did in the first two examples, to find the LCD. What is the LCD in this case? Well, the LCD needs to have an a in it, because look at all the fractions that I've got. I'm going to highlight all the denominators. Oh, not with that color. I'm going to highlight all the denominators. Here's one, here's one, here's one, here's one. Those are all the denominators within the numerator and the denominator. What's the highest power you see a raised to? There's a first and a second, so I'm going to put a second power there. What's the highest power you see b raised to? Alright, I see a square on it too. So there's my LCD. Now I take this times a squared b squared. I take this times a squared b squared, and I'm going to distribute that to each term in the numerator and each term in the denominator. Okay? Now what happens? When I take a squared, b squared times 1 over a. That a is up on top. Whatever, it doesn't have a fraction, it's understood to be over 1. So that a squared is on top. This a will cancel with one of these, leaving behind an a and a b squared. Now when I take a squared b squared times a over b squared, the b squareds completely cancel out, and I'll have an a times a squared, which is plus a cubed. In the denominator, a squared times a over b squared, same thing happens as just happened in the numerator. The b squares cancel. I'm left with a times a squared, which is a cubed, minus the a squares cancel. The b cancels with one of these b's, and I'm left with just a single b. Alright, now the question is, can I simplify that? Since I can't factor the denominator any further at all, then that is as simplified as this is going to be able to get. Alright, and thus ends section 6.3.